As I told you in the concluding remark of the previous video, that is, in this particular video we will be learning about the second most important instrument involving refraction. The name of that instrument is prism. Now prism is a wonderful object. So right now in this particular video we will be only learning about a monochromatic light being incident on the prism, and whatever deviation it actually gives us, we'll study only about that. That is, incident light comes in, emergent light goes out. We'll only study about the deviation it produces in the path. So let's find out how should we do that. So now let's study prism. That is one of the application of the phenomena refraction. So basically it's like lens, but I have two different orientation of lens. What do you mean by orientation? I will explain you when we talk about the prism one. So basically, we will first start off with refraction through the prism. So this is setup. That is, the prism looks like this: ABC, having a refractive index mu. Then there's an incident light which kind of undergoes refraction twice. That is, once going from A to the refracting surface, and the other one being from the refracting surface, that is glass or water, whatever, to air. These are the two normals of the surfaces. Angle A corresponds to the angle of prism. R1 and R2 are the angle of refraction. Now we'll simply do the geometry associated with it. That is, just try to learn what is the relation between the angles over here. So I've got I, R1, R2, E and A. And del is an angle of deviation based on my incident ray to my emergent ray. That is, I want to calculate how much of my incident ray has deviated from its original path. So we consider the quadrilateral APOQ, and A plus O definitely gives me 180 degree, because this angle, as you can see, is 90 degree. This angle as well is 90 degree. So angle APO and angle AQO, they are 90 degrees, because of which I have A plus O to be 180 degrees. Then obviously, since N1 and N2 are normal, I have those angles to be 90 degrees. In triangle OPQ, I have R1 plus R2 plus O is equal to 180 degree. That is simple. The sum of that each angle of triangle will add up to give me 180 degrees. That's the use of it. Now in triangle DPQ is with which we get angle of deviation del. Del is given by I minus R1 plus E minus R2. Now this is how we actually end up calculating angle of deviation. That is, the initial path was this, then the path taken was this. Okay, so this was the path taken. Now as this was the path taken, the angle of deviation is the first part, I plus R1. Now the ray is actually traveling like this. Now the path taken, the new path taken is this. Hence, now further angle of deviation comes out to be E plus R2. So the total angle of deviation comes out to be I plus E minus R1 plus R2. From 1 and 2, that is the two of the facts which we got from a quadrilateral and the triangle, is A is equal to R1 plus R2. That is both the angle of refractions, one for the initial angle, incident ray, and the other one acts as an incident for the other surface. So A is equal to R1 plus R2. Using this, we get that the angle of deviation is angle of incidence plus the angle of emergence minus angle of prism. A is the angle of prism specific to the prism we have, or I plus E is equal to A plus delta, to just give you a fancy look. That's it. So this is a very important property of prism, that is, it relates the two most important angles of our context in studying refraction through prism, that is E and I, angle of incidence and angle of emergence, to the basic properties of prism, that is, A is an angle of prism and del how much deviation it produces. Now we just need to first study the variation of deviation with the angle of incidence, and basically want to find out the minimum and the maximum and how it varies throughout my venture in changing the angle of incidence from 0 to, let's say, 180 degrees or even 90 degrees. So this is the variation which we have plotted. So we can clearly witness that there is some sort of minima into the picture. So and we get the minimum when angle of incidence is equal to angle of emergence. That is the minimum angle of deviation for a particular angle of incidence. So when an angle of incidence increases, the angle of deviation decreases. As you can see, when it increases, it kind of decreases and it reaches a minimum value. At a particular value of the angle of incidence, the angle of deviation becomes minimum and is called angle of minimum deviation. So this del m corresponds to what's being written in red letters. Now at del m, which is already given, I equals to E. Now using the previous property which we learned few slides back, R1 will come out to be R2, and let's say it's a constant R. So after minimum deviation, the angle of deviation increases with the increase of angle of incidence. So hence, as it's minimum, so across it, obviously if you move angle of incidence in either direction from this particular point, you will get a rise in angle of deviation. Refractive index of prism. Now, based on the different properties which I know of prism, that is angle of incidence, and with the special conditions, that is during the angle of minimum deviation, I have this particular thing because of R1 equals to R2. So I have R to be, R is basically R1 or R2, either way. So R comes out to be A by 2 and I plus E comes out to be A plus delta. And 2I comes out to be A plus del m. So basically we are putting the condition for minimum angle of deviation in all the entities which we know for the prism. So that's what we are doing. Why? Because I want to basically find out the angle of minimum deviation in terms of the parameters which I know of. I don't need to vary those things. Let's say angle of prism, or refractive index, whatever. So that's what we are doing. So with the help of Snell's law, I will do that. So mu is equal to sin I by sin R1. So in place of R1, I can write R. So in place of R, now I will put R equals to A by 2. And in place of I will put out A plus del m by 2. So I have this relation in front of me, that is refractive index is equal to sine of A plus del m by 2 divided by sin A by 2. So if you look closely, this is a property fixed or a constant property for a prism. Refractive index is also fixed for a particular prism, right? Whether you use a particular type of glass, refractive index is kind of fixed. So basically, the moment I pick up my prism, its minimum angle of deviation is already decided. It's independent of angle of incidence, whatever be the case. It only depends upon whether my prism is an obtuse triangle or a very acute triangle. Does it have a good refractive index, good as in high refractive index or a low refractive index? So these are the properties based on which an angle of minimum deviation is known. So please keep that in mind, it's very important. So refraction by a small angle prism for a small angle of incidence. So right now I have come up with generic sense, that is, this is how angle of deviation, minimum deviation, and refractive index and angle of prisms are related. Now we will pick up special cases. So this one over here is refraction by small angle prism for a small angle of incidence. That is, I am keeping the angle of prism small and also angle of incidence to be small. So sin I by sin R1, this comes out to be sin E by R2. Now here the assumption which I have placed for this particular setup. So in this particular setup, if I is assumed to be small, that is small angle of incidence, then R1 and R2 and E will also be very small. If I am starting off with small angles, so the minimum amount of deviation will be in multiples of the sine of their angle. So replacing the sines of the angles by angles themselves, because as they are small, see basically I is small. If I is small, then I can make sure that E, R, R1, R2, they will all be small because they are all related by refractive index. So finally we will get mu is equal to 1 by R1 and mu is equal to E by R2. Using the already known property, we can come out with I plus E is equal to mu R1 plus R2 is equal to mu A. So finally, putting out the values, we will get that angle of deviation comes out to be, for a small angle of incidence and a small angle of prism, comes out to be del equals to A times refractive index minus 1. That is, please keep in mind that the assumptions in play are small angle of incidence and small angle of prism. Only then we will land up with this expression. Otherwise, the expression given previously for minimum angle of deviation holds true for any type of prism or any type of angle of incidence. This is only a special case. Now let's try out a problem. A biprism of obtuse angle of 178 degrees is placed at a distance of L equals to 20 centimeter from a slit. How many images are formed and what is the separation between the images? Now, if I want to put up with the diagram, so the diagram kind of looks like this. So I have a biprism of obtuse angle 178 degrees. So let me put this up with an angle alpha, and I have an object over here. So the object will, so first light rays over like this, then the second one kind of comes out to be, let's say, like this, and the third one comes out to be like this. So I can make sure if I retrace this, this will be a point of the image and this will be the point of the image, this one. So I have S over here, S1 and S2, and it's given this is the distance L and this is the distance D. So basically, first, how many images will be formed? Obviously I'm going to get only 2 images. Now I need to find out what is the separation between the images. That is, finally I need to find out what is the value of D. Now, right, if I have known the angle of incidence, that the angle of prism, it's given to be 178 degrees. But once the light rays are actually hitting me, this becomes the angle of prism. Let's say this is theta. This becomes the angle of prism. So theta is basically equal to pi minus alpha by 2. Right? Because I know this is a biprism of obtuse angle, so it means theta is over, angle theta is like this over here, and same angle theta will be here. So theta for me will be pi minus alpha by 2. Now this theta is quite small, right, because this is 178 degrees. So even if I subtract, it will be close to an order of 1 degrees, right? So this is a small angle of prism, and also the angle of incidence will be kind of small. So the angle of deviation comes out to be angle of prism mu times 1. This will be the angle of deviation, because based on the assumptions we played out the sine terms and came across this angle of deviation. Now I also know that if this is the angle of deviation del, then del L, or del L, sorry, this is del, so del L will give me the value of d by 2. So finally I will come up with the term that is LA mu minus 1 multiplied by 2 will give me d. So if I put up with the values of mu, L, A and 2, the value of 2 is being 2, so d comes out to be approximately 4 millimeters. While going through the lecture, if you face any doubt, you can post your doubt for free at askIITians.com. In order to do so, you first need to navigate to the askIITians.com. Then, while going to that link, you can use discussion board link, which is over here. Clicking on this particular discussion board link, it will take you to a page where under the head of Ask the Experts, you can post your doubt under various categories. And the team of Ask IITians Expert will get back to you between 24 to 48 hours. So in this particular video, we just learned about a few aspects involving prism, that is monochromatic light being thrown at the prism, and we studied about different deviations which we get for the optical part for different incident angle and different emergent angle. We sort of got hold of the maximum deviation and the minimum deviation as well. So now that we are done with the half part of the prism, in the next video we will learn the other half of the prism. So let's find out what is that other half.